Good evening again. Welcome to the live session for the week one of Characterization of Construction Materials course. I welcome you all to this live session. Let's start the session in a few minutes. So, I'll just explain how it will go. So, I have a set of questions prepared based on the week one content of the CCM course. So, I'll share the screen. Make sure the screen is visible to you. There'll be a question on the screen. I'll also explain the question. So in the meantime, you can answer them in the chat box. Okay. Nikesh, can you explain what do you mean by reopen?
मैम असाइनमेंट की लिंक ओपन नहीं हो रही। कल ओपन किया था मैंने तो ओपन नहीं हुई थी, आज ओपन नहीं हो रही मैम।
Is the deadline over? No, right?
नहीं
When
नहीं
is the
मैम,
deadline?
डेडलाइन कल है 8 तारीख, 8 फेब।
8th or 8th
हाँ
Feb.
8 8 8।
Assignment 1 deadline is on 8th February.
हाँ मैम।
Yeah, then it should be open. It has to be open. Is it the same for all the others? Then I'll raise the issue to the NPTEL coordinator team. If
ओके
it
मैम।
is just for you, then you might have to try a different browser or try at a different time. Maybe the network is poor, something like that.
ट्राई किया मैम, आज दिन में ट्राई कर रहा हूँ, पता नहीं क्यों ओपन नहीं हो रही वो लिंक। कल
But
ओपन हुआ था वो।
yeah, but we have not received such a issue from anyone else. So that's might be your system issue or your browser issue, maybe. Anyway, try it again. We have,
ओके मैम।
yeah, tomorrow is the last date, right? Okay. Okay. So let me try to share the screen.
ओके मैम, प्लीज रीसेंड लिंक।
Yeah. Is the screen visible to you? No.
No, ma'am.
One second. Yes. Is the screen visible to you now?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So I'll just adjust it such that I can see the chat box and also the question screen. So yeah. So this is a characterization of construction materials course, and in the week one, it was just an overview. We didn't go in detail about the construction techniques. Instead, we just introduced what are the different construction materials which we will be dealing with, right? So, for example, we read about or we professor talked about uh, cement, different composition of cement, then concrete, and also steel, polymers, asphalt, etc. So, from all the content which was shared in week one, we have a few questions. So, I'll share the question in the screen in the PPT form, in the slide form. You can see the question. I'll also explain the question through mic. So whichever you see as a right answer, you can mention it in the chat box. Okay. So moving on to the first question. As per the cement chemistry notation, F denotes option A iron, option B FeO, option C Fe2O3, and option D Fe3O4. Okay, thank you, Srish. Srish has told that it is option C. Okay, I'm waiting for the others' replies. Chaman has also replied that it is C, which is Fe2O3. We have 8 attendees in the meet. So if you can respond in the chat box or through mic, it'll be good. Okay, Sneha. So I guess majority goes with the option C, and which is fairly easy. So the correct answer is C. So as we know, cement chemistry notations are quite different from the usual chemical notations of elements. So C is not carbon, it is calcium oxide as per the cement chemistry notation. Similarly, S is not sulfur, it is silica or silicon dioxide. And alumina is A. F is Fe2O3 and it is not iron, Fe. Okay, so this is just a screenshot from the slide of the professor. So F here indicates Fe2O3. Okay, thanks all for those who have responded, and those who are resisting to respond, please do respond in the chat box. Let's try to learn together. So, okay, moving on to the next question. The hydration product which regulates the alkalinity of ordinary Portland cement concrete is dash. CSH, CH, Ettringite, or gypsum. So we know that in ordinary Portland cement concrete, it has a higher alkalinity. It has a high pH. And what is the ingredient of the ordinary Portland cement, or what is the hydration product in the ordinary Portland cement which causes higher pH or a higher alkalinity? Option A, CSH. Option B, CH. Option C, Ettringite. And option D, gypsum. So, which is the hydration product which regulates the alkalinity? Okay, Shrish and Chaman had commented that it's option B or CH. So, what is CH? Can someone type in the chat box? What is CH? Yes, Portlandite or calcium hydroxide. So, anyone else wants to comment? Is it CSH, CH, or Ettringite or gypsum which regulates the alkalinity? Okay, I guess that is the response I'm getting. No more responses. Okay. Anyone else? Okay. So it is calcium hydroxide or CH or Portlandite which provides the alkalinity or which results in the higher alkalinity of ordinary Portland cement concrete. It's not CSH, Ettringite or gypsum, it is calcium hydroxide. You must be quite familiar if you have taken basic courses about about concrete technology or even advanced levels of concrete technology, that calcium hydroxide provides the basicity or alkalinity to the ordinary Portland cement concrete. Thank you, Shri and Chaman, for responding in the chat box. So let's move to the next question. The phase of the cement, which contributes to the early strength and stiffening, and which has a high heat of hydration also. The phase of cement, which contributes to early strength and stiffening and has a high heat of hydration. C3A, C3S, C2S, or C4AF. C3A is tricalcium aluminate, then tricalcium silicate is C3S, C2S is dicalcium silicate, and C4AF is a tricalcium aluminoferrate. So again, Shrish and Chaman have gone with the option A, that is C3A. Let's wait for a minute for hearing other opinions as well. Okay, Sneha also goes with C3A. Ganesh, okay, goes with A. Okay. Does anyone else wants to respond? Okay, Mehna goes with A. Okay, now let's move to the correct answer. The correct answer is option A. So C3A is responsible for the early strength and stiffening. Okay, so C3 is also, but it's responsible for early strength and but more than that, it's a C3A which has a very high strength and also contributes to early stiffening. Okay, moving on to the next question. Dimensional stability of a concrete is attributed to the aggregates present in it. State true or false. So, any concrete structure has got its dimensional stability. So, aggregates are a reason for the dimensional stability of a concrete. State true or false. Okay. So, Shreesh, Chaman, and Ganesh had gone with true, and Sneha as well. Excuse me. Okay. Let's try to move to the correct answer. Correct answer is A, which is true. That is, aggregates are responsible for the dimensional stability because spaced it can be deformed and it binds the aggregates and the particles in the concrete, whereas aggregates cannot be deformed and they provide the stability in dimension for the concrete member. So let's move to the next question. Okay, this is related to more related to characterization. In the backscattered image of an ordinary Portland cement concrete, pores in the hydrated cement paste are dash color and unhydrated cement grains are dash color. So X and Y. So identify X and Y. So X is black, Y is white. Then X is white, Y is black. Then X is gray, Y is white. Then X is black and Y is gray. Okay, Srish went with option C, Chaman with option A. Okay, now this is the first question with different opinions. Okay, Srish also changed to A, Ganesh A. Okay, so now everyone goes with A. Do we have any other difference of opinion from someone? So make sure you understand what feature we are referring to here. One is a pore, the other one is an unhydrated cement grain. Also, it's a backscattered imaging. So far we have received only three responses. What happened to others? It's okay even if the answers go wrong. Try this as a practice session. Consider this as a practice session. That's all the response I'm going to get, I guess. Okay, so let's move to the correct answer. Correct answer is A. So here, this is also a snippet from the slide. So if you see, there is a black color semicircle, which actually is a pore. So what happens in the backscattered imaging? It provides the image based on the density difference of the material. So obviously in a pore there is nothing to scatter back. So as a result of which it shows in black in color, whereas cement grains are much brighter. It's very highly dense, it is much brighter. So what happens? The denser phase, that is a cement grain, will be shown in a white color. All the other hydration products or voids, anything, not the voids, hydration products, they'll be having a density ranging from the density between a pore and that of an unhydrated cement grain, as a result of which they will be shown in different shades of gray or ash. So here all these white small elements are unhydrated cement grains, and the black one is a pore. Keep that in mind. So pore is black in color and an unhydrated cement grain is white in color in the case of a backscattered imaging. Okay, so the correct answer is A. Thank you guys for responding. Now moving on to the next question. The pores present within the hydration products in the ordinary Portland cement concrete are known as X. Identify X from the options given below. What is X? Are they air voids, or are they gel pores, or are they capillary pores? So here we told that the pores are black in color, but pores exclusively within the hydration products, what are they known as? Are they air voids, or are they gel pores, or are they capillary pores? Okay. Sri has commented that it is gel pores. Okay, let's wait for more response from others. Okay, Ganesh told it is capillary pores. Okay. Anyone else? Okay, I'll wait for a minute. Let me see. Please feel free to respond in the chat box. Even if it goes wrong, it is okay. That's all. No one else is planning to respond. Okay, so we have got two options, gel pores and capillary pores as answer. So let's move to the correct answer here. Okay, so the correct answer is option B, that is gel pores. Okay, so here this is snippet again from the slide. So the third point, if you see, hydrated cement paste is composed of capillary pores and hydration product. The pores within the structure of hydration product, it is known as gel pores. Okay, so within the hydration product, that is say CSH. Okay, within the CSH there are so many pores that they are known as gel pores. But outside the cement paste, or sorry, outside the hydration product, that is within the cement paste itself, other pores are there and they are known as capillary pores. So cement paste is composed of two types of pores. One is a capillary pore and the other one is a gel pore. Okay, so next question is also related to, yeah, it's related to pores itself. So with reference to the previous question, so you remember the previous question, right? So what is the pore which is present within the hydration product? So according to Powers, what percentage of the total pores are X? So you should know what is X. So X is now gel pores. So according to Powers, what percentage of the total pores are X? 25 percentage, 50 percentage, 33.33 percentage, or 66.66 percentage. Okay. Shrish commented that it is C, that is 33.33 percentage. Excuse me. Okay, Sneha also commented it is C. Okay, let me wait for a little more. Ganesh also commented it is C. What about others? Does anyone say it is 66.66? Okay, I'll wait for less than a minute, maybe. Yeah, I guess not sure. Okay, let's see. Okay, so let's move to the correct answer. The correct answer is C, that is 33.33%. So, from the snippet of the slide, you can see that according to Powers, one third of the pore space is comprised of gel pores and the rest are capillary pores. So, 33.33 will be gel pores and 66.66 will be capillary pores. Okay, of all the pore spaces, one third is gel pore and two third is capillary pore. So I hope that is clarified. The correct answer is C, 33.33%. Okay, moving on to the next question. Tar dissolves in gasoline, whereas asphalt does not. Stay true or false? The question is tar dissolves in gasoline, whereas asphalt does not. State true or false? Okay, Ganesh and Shrish goes with true. Chaman also goes with true. Sneha goes with true. Okay, let me wait for a little bit more time. Okay, the correct answer is false. Okay, there's a new person. Okay, he or she had gone with A. Okay, what's your name? I couldn't get it. The newly joined one. Can you type your name? Like how I should call you out? Yeshu Kumar. Okay, fine. Thank you. So, this is the refining stages of asphalt. So, from liquid gas or propane, it becomes naphtha, then petrol, then kerosene oil, grease, and then it becomes asphalt. So, it has been refined from gasoline, which means that it can further dissolve in gasoline also. That is why, in the case of asphalt pavements, suppose there is a petrol dripping from some vehicle, because of that, the asphalt can dissolve in that petrol, and that particular area of the flexible pavement or the asphalt pavement can deteriorate. That is because the asphalt layer, if there is no top surface layer protection layer, if it is just asphalt, then it can dissolve in the gasoline and deteriorate the pavement. So that is why uh, the asphalt tends to deteriorate in the presence of gasoline or when gasoline falls over the asphalt layer. So the correct answer is B, which is false. Okay, moving on to the next question. Suspending asphalt in water using an emulsifying agent dash. It increases the viscosity of the asphalt, it decreases the viscosity of the asphalt, or it does not alter the viscosity of asphalt. So, what does asphalt suspension in water using an emulsifying agent do? Does it increase the viscosity? Does it decrease the viscosity? Or it does not alter the viscosity of asphalt? Okay, Chaman goes with does not alter. Shrish and Ganesh goes with decreases the viscosity. Okay, now let's wait to hear others' opinion. Okay, Yeshu Kumar goes with increases the viscosity. Okay, any other response? Any other opinion from others? Okay, we have new joinees. Anyone? What about Javed, Mehna, Nikesh, Harshita? I'm just calling out names which I have not seen in the chat box. So don't worry. So the question is pretty simple. Using an emulsifying agent, if you just suspend asphalt in water, what does it do? Does it alter the viscosity? Option A says it increases the viscosity. Option B says it decreases the viscosity. And option C says it does not quite alter the viscosity of asphalt. And we have got all the three options as answers from the chat box. So, yeah. Okay, without further ado, let's move to the correct answer. The correct answer is that it decreases the viscosity of the asphalt. So it becomes much more easier to work with if you decrease the viscosity. So if you see the asphalt properties slide, the second point indicates techniques to lower viscosity, and the second one is a making an emulsion. Okay, so keep that in mind. If you make it an emulsion, by suspending asphalt in water using an emulsifying agent, then it decreases the viscosity. Okay, so moving on to the next question. Crude oils, they're considered to be asphaltic when the asphalt content is greater than 60 percentage, greater than 50 percentage, greater than 70 percentage, or greater than 55 percentage. So we name crude oil, or we refer to crude oil as asphaltic if the asphalt content is greater than 60 percentage or 50 percentage or 70 percentage or 55 percentage. Okay, just Shrish has commented that we call them as asphaltic if it is greater than, if the asphalt content is greater than 60 percentage. Okay, Ganesh commented that if it is greater than 55 percentage, we call them asphaltic. Okay, who else? Excuse me. Okay, Yesh Kumar says it is greater than 50 percentage. Okay, anyone says it is greater than 70 percentage? Okay, let's wait for a few more seconds before going to the correct answer. Excuse me. Okay, let's move to what the correct answer. The correct answer is option A, that is greater than 60 percentage. So if you see here, this is a snippet from the slide. So crude oil, it's paraffinic if it has 0 percentage asphalt, and if it is having a 60 percentage asphalt or more, it's known as asphaltic. And if it is 6 to 12 percentage asphalt content, then it is a mixed crude oil. Okay, so keep that in mind. If it is 60 percentage, greater than 60 percentage, then the crude oil is known as asphaltic. Okay, let's move to the next question. To get a homogeneous asphalt concrete mix, the placement temperature must be between 70 degrees Celsius to 80 degrees Celsius, or 80 to 100, or 100 to 125, or 125 to 150. So this is regarding the placement temperature of asphalt concrete mix. What we all need is a homogeneous mixture. We don't want uh, lumps. We don't want heavy viscous and then changing to low viscous, etc. What we need is a homogeneous mixture. So to get a homogeneous mixture, the placement temperature has to be between 70 to 80, 80 to 100, 100 to 125, or 125 to 150. I'm waiting for responses. Anyone? Okay, now I'm confused. Who? Okay, Yeshu Kumar commented it has to be between 100 and 125. Shrish comments it's between 125 and 150. Okay. Ganesh goes with 80 and 100. Okay, interesting. So, anyone for option A? What about the girls? I'm not seeing anyone in the chat box. Suddenly, some used to answer. What happened to them? Where is Mehna, Harshita, Sneha? Okay, let's give them a few more seconds. Okay, let's move to the correct answer. The correct answer is option D, between 125 and 150 degrees Celsius. Okay, to get a homogeneous mixture, the temperature has to be between 125 and 150 degrees Celsius. Okay, let's move to the next question. No, with reference to the previous question. So, it's regarding the placement temperature of asphalt concrete. At that range of temperature, asphalt exists as glassy solid, viscoelastic liquid, or Newtonian fluid. So you know now that the temperature range which we are talking about is 125 to 150 degrees Celsius. So what is the state of asphalt at that temperature? Is it a glassy solid, or viscoelastic solid, or viscoelastic liquid, or Newtonian fluid? Okay. So Chaman went with viscoelastic solid. Okay. Thank you for responding in the chat box. What about others? Okay, now everyone goes with viscoelastic solid. Mehna and Sneha. Ganesh also goes with viscoelastic solid. Shrish goes with viscoelastic liquid. Okay. Okay, I think we have given enough time to answer. So let's move to the correct answer. Okay. The correct answer is Newtonian fluid. Because before itself we have told that it has to be a homogeneous mixture, and more than that, we do not want any other stress strain relationships. We want it to be like a Newtonian fluid at that range of temperature, that is 125 to 150. All the solid phase, it will happen at a very lower temperature. From glassy solid to Newtonian fluid, there is a transition of asphalt that happens from even from 0 degrees Celsius. So to less from less than 0 degrees Celsius to more than 100 degrees Celsius, asphalt changes its form from glassy solid, then it becomes viscoelastic solid. Then we are increasing the temperature. So if you just imagine, if you are increasing the temperature, there's a tendency for it to go from solid to liquid. It kind of melts, kind of melting. So then it changes from viscoelastic solid to viscoelastic solid to viscoelastic liquid. Then finally it becomes a Newtonian fluid. So the correct answer is option D. Okay, let's move to the next question. The fatigue resistance of asphalt concrete pavement increases with the load repetitions. So this is quite interesting, right? When the number of load repetitions increases, we think it will wear and tear. That set apart, the fatigue resistance of the asphalt concrete also tend to increase. Why does it happen so? First thing, binder hardness increases. Secondly, aggregate hardness increases. Or air voids between the binder and the aggregate, they collapse or they decreases. Or option D, asphalt changes from viscoelastic solid to a glassy solid. Okay, let's see. Okay, Shrij and Chaman went with option C, that is the air voids between the binder and the aggregates decreases. Okay, anyone else? Okay, Javed goes with aggregate hardness increases. What about others? Anyone else? Ganesh goes with binder hardness increases. Okay. Okay, so just let's move to the correct answer. Correct answer is option number C. See, the binder hardness, it cannot change, and aggregate also, it its hardness, or it is something which does not undergo a change of properties if you keep on increasing the load repetitions. So what logically can happen when there is number of load repetitions increase is that there will be some air voids between the aggregate and the binder. Those will collapse, or the gap becomes lesser and lesser. So the air voids tend to decrease with the number of load repetitions. So as a result of which, the fatigue resistance of the asphalt concrete increases with the load repetitions. So the correct answer is option C. So those who have told other options, please stay corrected. So fatigue resistance of the asphalt concrete, it increases with load repetitions because the air voids between the binder and the aggregate decreases. Okay, so let's move to the next question. How much percentage of carbon is present in alpha iron at room temperature? So it's pretty straightforward question. Uh, in alpha iron at room temperature, how much is the percentage of carbon? Is it 50 percentage, 0 percentage, 65 percentage, or 67.7 percentage? It's a pretty straightforward question. Not much of logic or not much of thought need to be put to answer this. Okay, Chaman goes with option B, that is 0 percentage. Okay, anyone else? Okay, Shrish also goes with B, that is 0 percentage. Okay, or D, I'm confused. I mean, I think it's just a human brain that when you see something which is not affirming to the other options, 67.7 percentage, where did it come from? So I get where the confusion comes from. Okay, let's see. I'll wait for a few more seconds. Okay, I think that's all I'm getting. Everyone else seems to be confused. So the correct answer is option B. It's D is not the correct answer. It's option B because at room temperature, it is the purest form of iron, that is alpha iron. It has no carbon content, or even if it is its very minute level carbon content, and we can say 99 percentage cases there is zero carbon content in the case of an alpha iron. So it is a purest form of iron, alpha iron, and at room temperature there's no carbon content in it. That is 0 percentage. Okay. So moving on to the next question. What material property is introduced by the addition of carbon to iron in the manufacturing of steel? So, is it malleability, ductility, toughness, or hardness? So, it's about the property which gets introduced by the addition of carbon to iron in the steel manufacturing process. Is it malleability, ductility, toughness, or hardness? So, Shrish again commented it is D, hardness. Okay. Anyone else? So basically, what he says is that by adding carbon, we are improving the hardness, or we are imparting hardness to the iron or the composite. Okay, Chaman also goes with D, hardness. Okay, Ganesh also goes with D. Anyone else? Okay. Okay, let's move to the correct answer. I think it was a pretty straightforward question. So the correct answer is D. By introducing carbon into iron in the case of a steel manufacturing, we are introducing hardness to the system, or we are giving more hardness to iron when you add carbon to it. Okay, so let's move to the next question. So, which of the following phenomena occurs at the eutectoid point? So, eutectoid point is that point where something of A, B, C, D happens. So, option A, one solid transforms into two different solids. Option B, one liquid transforms into two different solids. Or one solid transforms into two different liquids. Or one liquid transforms into two different liquids. Okay. So, Shrish commented it is one liquid which transforms into two different solids. Okay. Let's hear from others also. I'm just waiting to listen to others' opinions. Okay, Ganesh goes with D. That is liquid to two different liquids. Okay. Okay. Who else? Trish, Ganesh. There are 8 others at least in the group who are attending the session. So please feel free to answer. So eutectoid point is the point at which something happens, some transformation happens. So what is a transformation? Wait for a few more seconds before discussing the answer. Okay, Chaman mentioned A. Okay, anyone wants to go with C? We have received A, B, and D. Okay, I guess that's it. No one else is going to reply. Okay, so the correct answer is option A. That is one solid transforms into two different solids. That is eutectoid point. I'm not showing any reference here because the next question is also related to eutectoid point. So here is a question. So this particular phase diagram everyone are quite familiar with because there's just the same diagram which was discussed in the class. So refer to that diagram and answer the following question. Choose the weight percentage of carbon in the iron carbon solid solution at which the eutectoid transformation occurs. 0.77 percentage, 4.3 percentage, 2 percentage, or 6.7 percentage. Okay, I think I have. Okay, Chaman, Shrish, and Mehna went with option A, that is 0.77 percentage. Okay, waiting for others to respond. Okay, that's it. Okay, so the correct answer is option A, that is 0.77 percentage. So here you can see that is a eutectoid point, that is 0.77 percentage or weight percentage of carbon in iron, then you will get the eutectoid point. So the correct answer is option A. Thank you guys for responding. Now, moving on to the next question. Which is the correct arrangement of iron carbon phases in the increasing order of their ductility? So, read carefully. It's about ductility, and there are different iron carbon phases given: martensite, pearlite, spheroidite. So they are arranged in different orders. So which is the correct order, which shows the increasing order of ductility? So according to option A, least ductile is martensite and most ductile is spheroidite. So that's how we read option A. And according to option B, least ductile is pearlite and most ductile is again spheroidite. According to C, least is spheroidite and most ductile is pearlite. According to option D, least ductile is pearlite but most ductile is martensite. I have not received any response, I guess. Yeah. Okay. Shrish goes with A. Chaman goes with A. Who else? Ganesh goes with D. Okay. I'll give a few more seconds for others to answer. Anyone else? So I have two option A's and one option D. Okay, so let's move to the correct answer. Correct answer is option A. So this again is snippet from the slide. So here ductility arrow goes down. So it's a general trend. Spheroidite is very ductile, and in the middle comes perlite, and martensite is least ductile. It has a higher strength though, but according to ductility, if you see, spheroidite is most ductile and martensite is least ductile. So the correct answer is A. Okay, let's move to the next question. Now match the following. So the options are here. First column is perlite, bainite, and martensite. Second cooling is rate of cooling from austenite. Okay, so something by rapid cooling, something is by slow cooling, and something is by moderate cooling. Option A, how to read this option? Perlite is by moderate cooling. Second one, that is bainite, is by slow cooling. 3A, that is martensite, is by rapid cooling. That is option A. Similarly, there are three more other options. So let's see who answered. Okay, Shrish answered option B. So he says, okay, one second. Ah, he says one is B, that is perlite is by slow cooling, bayonet is by moderate cooling, martensite is by rapid cooling. Right? Yeah, that's what he says. Okay, yeah. Anyone else wants to comment? Okay, Chaman also goes with option B. Ganesh goes with B. Okay. Anyone else? Mehna? I think her name was Mehna. Mehna, right? Yeah, Mehna. Anyone else who has a difference of opinion or wants to confirm that it is B? Option B. Okay, let's move to the correct answer. Yeah. So the correct answer is option B. So austenite, it's a gamma. It undergoes slow cooling to form perlite. It undergoes moderate cooling to form bainite. And it undergoes a rapid quenching or rapid cooling to form martensite. And when it is reheated, it becomes a tempered martensite. Okay. So slow cooling perlite, moderate cooling bainite, and fast cooling or rapid quenching is martensite. So this correct option is option B. Okay, let's move to the next question. The 415 in Fe 415 indicates the yield strength. Say true or false. So it's very easy question. Okay. Chaman, Ganesh, Shrish, everyone goes with true. Okay. Yes, the correct answer, because I don't think I have to wait any more for any more response. Okay. Everyone, the correct answer is A. That is Fe 415, and 415 is the yield strength. Okay. So let's move to the next question. The tempered martensite layer has a better corrosion resistance than the ferrite perlite layer in a QST rebar. State true or false. So, the tempered martensite layer has a better corrosion resistance than ferrite perlite layer in a QST rebar. Okay, I'm waiting for some response. Oh, okay. I don't know. 6:58 p.m. I think Javed and Chaman replied for this question. I hope. Okay, Ganesh goes with false. Sri so goes with false. Okay. Okay. So let's move to the correct answer. Correct answer is true because in the case of a QST rebar or quenched self-tempered rebar, the outer layer is a tempered martensite layer and the inner layer is a ferrite perlite layer. The outer one has a higher strength and corrosion resistance because the outer layer has to be more corrosion resistance than the inner layer, right? Because it is from the outer layer that the corrosion proceeds or progresses further inward. So it is desirable that the outer layer has a better corrosion resistance than the inner layers. So the tempered martensite layer has a better corrosion resistance than the inner ferrite perlite layer. Okay, let's move to the last question for today. That is, which of the following is the correct arrangement of polymer configurations in the increasing order of their Young's modulus? So I'll read the question again. You have to arrange the following polymer configurations in the increasing order of the Young's modulus. So which has a higher Young's modulus? So according to option A, network has least and linear has more. According to option B, cross-linked has least and network has more. According to option C, linear has least and network polymer has more, the higher Young's modulus. According to option D, it is network which has least and cross-linked which has more. Okay. So okay, I think I have got many responses. So okay, everyone goes with option C. That is linear less than cross-linked less than network. Srish, Chaman, Sneha, and Ganesh, thank you for responding. I'll wait for 1 more minute. Okay, Javed goes with D. Ganesh goes with C. Okay, okay, he goes with A. Okay, so let's move to the correct answer. The correct answer is C. That is, as the crystallinity increases, uh, the Young's modulus is also increasing, or crystallinity increases, E also increases. In that case, network is having highest Young's modulus, then comes the cross-linked, and last comes the linear. So, linear less than cross-linked less than network. Okay, so thank you for being here and for being wonderful student audience. Let me stop the recording.